Hello and welcome to this session on the training about PLAXIS Automation Basics, in which we will see how automation is handled in PLAXIS Output program. In this session, we will check Output's command line, figure out what are the objects and commands available, such as the result types, the face object, the plots, how to use the export command, and most importantly, how to retrieve results via the command line. Finally, at the end of the session, we will see a couple of examples in which automation makes our workflow more efficient. Let's start with Output's command line. Output's command line uses the same structure as an input, but most actions are not directly translated into commands. With the Output graphic user interface, we usually change the plot we are looking at, for instance, deformation, stresses or forces, etc. And we request large tables with results or more generic information. In general, requesting data through the command line is supposed to be more specific. You can have one command to retrieve one specific result for a single location, a pre-calculation or post-calculation node or stress point, or information for all nodes and stress points. Output has also a detailed documentation that you can find under Help Command Reference menu option. There, you can find all available commands and objects and the exact syntax to be used with examples. Note that you can use the echo and info commands to learn about object data structure in Output too. Let's begin with our first output object, the result types. Almost all results are accessible via the result type object. For example, for soils, it is resulttypes.soil. For plates, it is resulttypes.plate. For embedded beams, it is resulttypes.embeddedbeam, and etc. Each result type contains references to all available results in nodes and stress points. For instance, for vertical displacement in PLAXIS 2D, UI is resulttypes.soil.uy. For excess pore pressure, it is resulttypes.soil.pxs. The resulttypes.soil allows to see possible result types for soil elements. You can also use the echo command on the resulttypes.soil in Output's command line to see all the available results. Note that Python, unlike the PLAXIS command line, is case sensitive. To get the vertical displacement for PLAXIS 2D, you need to request resulttypes.soil.uy, making sure that soil is not with small letter s or the UI with a small letter u. For structural objects, the idea is the same. For instance, the resulttypes.plate allows to see all possible result types for plate elements. Remember that the command and objects reference is structured in a tabular form, and you can find detailed information for all the properties available. You can see an example of the plate output properties on the right side of the slide. Let's check another important object in Output, the face object. The face object contains general information about the face in your project. It contains a list of steps as a listable, which is accessible as face x n for the nth step of face you are currently checking. The face x.reached contains general results of the face, such as face x.reached.summstage, .summsf, and time. The face x.input settings contains general settings of the face, for example, ignore adjoint behavior, use updated mesh, use updated water pressures. For the full details, run the command echo facex. The moment you open PLAXIS Output to view the results of a project, you already see the plot object showing the deformed mesh. The plot object contains the visualization itself for soils, structures, interface, etc. It can be used to export to a file or a Python image object. Note that the main intention when using the plot object is typically for Python scripting handling. That is, as not all actions are always directly visible in the graphic user interface, GUI. Some examples of attributes are result type, plot type, for shadings and contour lines, face and step, draw frame, draw title, especially when exporting and saving the plot. More available can be found via the commands info plots -1 or echo plots -1. You can find more detailed information in our object reference if you search for the keyword plot. The page in this slide will appear, which includes all the available properties for the plot object. Time for some examples using the plot object. In this slide, you can see how to change the various properties of the plot object. For instance, if I want to change the result type, I need to run the command set plots -1 dot result type result types.soil.uy. To change the plot type for an individual object, set plots -1 dot plot type contour lines. To set up which face to use in exporting the plot, I need to set the face object. Set plots -1 dot face face 5. To adjust the mesh settings, I can run the following: set plots -1 dot mesh settings dot phreatic level false, that is to hide the phreatic level. Set plots -1 dot mesh settings dot fixities true, to show the fixities in the plot. Also, to change the available legend settings, I need to run set plots -1 dot legend settings dot intervals 10 for the intervals to be considered, set plots -1 dot legend settings dot min value -4 for the minimum value in the legend. In this slide, I have now written the same commands as before, but using the syntax for Python. As you can see, a big change is that I do not use the set command, as in Python I can directly use the equal sign, which allows me to assign the setting to objects. So for instance, in the first case, if I want to change the result type, I need to type go.plots -1 dot result type equal sign go.resulttypes.soil.uy. The same goes when wanting to set up the plot type to shadings, or setting the face object to face 5. Configuring the mesh settings and the legend settings is done in a similar way. Even though the soil or rock results are the first to inspect, PLAXIS offers many options for structural objects too. The command structure plot creates a new plot object with a selected structure. To run this, you need the command name and the structural entity. This structural entity can be plates or interfaces as a whole group, plate 1 or positive interface 1, plate 1,1 or plate 1,1,0. Here, inside the square bracket, we indicate that we want to create a plot viewing the first element. Remember, everything is zero based, and that of the plate 1,1. At the bottom of this slide, you will see an example of the PLAXIS command and the equivalent Python command. When handling any project, it is common to create cross-sections to better inspect our results. The line cross-section plot creates a cross-section in a new plot object in PLAXIS 2D. Here you can see an overview of the command syntax. The line cross-section plot is the command name. The plot is the current plot of the model, for instance the deformations plot. And the coordinates is a set of the two coordinates indicating the first and the second point of the cross-section. Note that this command is usually combined with the get cross-section results command that we will see later in this session. The equivalent command in PLAXIS 3D is called cross-section plot, and it creates a surface cross-section in a new plot object. The syntax is similar to the one of PLAXIS 2D, with the addition of a third component in the coordinates for the z coordinate. You can see an example at the bottom of this slide. When working with plots, it is common to wanting to export this to a file and adding it to a folder or a report. For this, the command export can be used to export to a file or a Python image object. The syntax of the command requires the command name, export, the plot, which is a reference of the plot object we want to export, the file name, which is the full path of the file to store with the extension .png, and optionally the width and the height in pixels. Note, for a Python image object, the file name should be omitted. PLAXIS output can provide various interesting plots, but the most important outcome of a calculation is the results. The most relevant commands for querying results via the command line are the following. Get single result. This command displays the result at a specific coordinate of a specific node or stress point with or without result smoothing. Get results. This command generates a table with the calculation results for all available nodes or stress points. Add curve point. This allows us to select stress points or nodes for calculation results with an indication of a preferred direction. Get curve results. This command allows us to display results for curve points that have already been selected. Get curve results path. This one displays results for curve points that have already been selected, but for several different phases. Get cross-section results. Finally, this command generates a table with the calculation results of a cross-section. Let's see them in more detail. To begin with, let's check the get single result command. This command allows us to retrieve a single result from a given location. The command syntax has the following parts. The command name, get single result, the reference to a phase or a step, the requested result type, and the location, which can refer to any coordinate, or alternatively, for post or pre-selected node or stress points, for instance, CN1 or CS1. Optionally, a boolean, such as true or false, can be added to use interpolation included adjacent elements for result smoothing. This command returns one value. You can see an example at the bottom of this slide. Moving to a more generic command, the getResults command allows to retrieve the specified result for all nodes and stress points. The command syntax has the following parts. The command name, getResults, the reference to a phase or step, the requested result type, and a string specifying node or stress point, which is used to retrieve results for a node or a stress point. This command returns a list of result values. The order of this list is per element number, per node, or per stress point. In the example below, you can see the command for phase 6, querying the results for total deformations on nodes. I then echo the results -1, which points to the lastly created results list, and I can see the full list of values. In the same manner, I can write the commands in Python. In this slide, you can see the case in which the getResults command is used for retrieving results for a structure. The steps to retrieve results are running the getResults command for a specific structure, for instance plate 1, finding the relevant result type, for instance result types.plate.m2d, and finally echoing the generated list of objects or results -1. An example of such case is shown at the bottom of this slide. Before we explain the next command for results, we need to see how we can select curve points in PLAXIS Output via the command line. The add curve point command selects nodes or stress points for curves by finding the nearest node or stress point to the provided location. The command syntax has the following parts. The command name, add curve point, a string specifying node or stress point to add the curve point which will be used to retrieve the results from, and the location by using coordinates. Optionally, before the location, one can add the name of the cluster or structure you want to select the node or stress point for. At the bottom of this slide, you can see an example for selecting a node and a stress point as a curve point. The general workflow we typically use starts from input program. We call output to open the curve point selection. We select the curve points using the add curve point command. We update output, which closes it, and then continue with our input program. In the provided example, you can see the series of commands used in such case for the PLAXIS command line and in Python syntax. Any selected curve points are stored in the curve points object as a listable. It is possible to select unlimited number of points for curves. The curve points object includes detailed information per curve point. Also, you can use the curvepoints.nodes or curvepoints.stressPoints to access them per curve point type. In order to clear all curve points, use the command clear curve points, followed by no parameters. The following two commands allows us to retrieve data for pre-selected nodes and stress points. The command syntax for both commands has the following parts. The command name, getCurveResults or getCurveResultsPath, the curve point which refers to the selected node or stress point, the phase or step information, and the requested result type. The getCurveResults returns the value of the selected result type for the selected point at the final step of that phase or the selected step. The getCurveResultsPath returns a listable object with the results for the selected point for the range of phases or steps. In this slide, you can see examples of both commands in the PLAXIS command line and in Python syntax. As mentioned in a previous slide, when creating cross-sections, it is logical to require to retrieve the relevant results too. For this, the command getCrossSectionResults is provided. The command syntax has the following parts. The command name, getCrossSectionResults, the plot, which is a reference to a cross-section plot object, the reference to a phase or step, and the requested result type. Optionally, a boolean, being true or false, can be added to use interpolation, including adjacent elements for result smoothing. This command returns a listable object with the results for the cross-section. In this slide, you can see examples of the command in the PLAXIS command line and in Python syntax. Note that in order to use this command, it is necessary to have created a cross-section, for instance via the line cross-section plot for PLAXIS 2D or the cross-section plot for PLAXIS 3D. Having seen all the available objects and commands for PLAXIS Output, we realize that even though they are great, we actually need more interaction with the program overall. We may have noticed that we did not have much interaction with the data itself. The results are only available in the command lines session. For instance, the getResults command gives a full list of result values accessible in the command line session only. It is not possible to use the results or the values or any other arithmetic expressions. There are no conditional expressions, if, case, or loops, no use of external libraries, and no way of exporting to files or spreadsheets. Also, currently, there are limits on the command line capabilities, for instance, in which generating curves is not supported. For this, we can use Python and remote scripting. Let's see our first example with Python. Here, we want to show a table for X, Y, UX, and UI for phase 1 on the screen. To retrieve the results, noted as R underscore, we should get the results for each result type. This is done on these 4 lines of code using the getResults command for each case for this phase. Now that we have run this and assigned them to variables, we have 4 lists with results. We can use Python's built-in function zip to loop over all results and print them in a nice tabular form. Here we go. We managed with just a few lines of code to create the full table covering all coordinates and deformations for this phase. In the second example, we will see how to retrieve bending moments along a wall at x equal to 20. First, we need to define a variable and assign the value 20 to it. Then we can run the getResults command for each coordinate and the m2d, which is the result type for the bending moment in PLAXIS 2D. With the same logic as before, we can use the zip function to loop over and zip the results together. Notice here that I add an extra line of checking for the specific coordinate. The print is only run if this if statement is satisfied. This means that we get to print only the values at x equal to 20 within some provided tolerance. In this last example, I would like to create a curve for time versus displacement from Cn1. Here, CN1 is the first curve point node that I have already pre-selected. I define two variables, times and uwise. I run a for loop for all available steps of phase 1 and I do the following append: the reach.time property of each step and the vertical deformation for the pre-selected curve point. Then, to be able to create a plot, I will use the matplotlib module to set up the two axes, the titles, and finally show the plot. And here's the time displacement curve I created with only a few lines of code. To assist you when working with PLAXIS and Python, we have created a scripting reference. This is available for both PLAXIS input and output. To see the examples for every command, you can start from the input program. Select Help, Scripting Reference menu option, start the input server, then the documentation Jupyter Notebook launches on your internet browser, and make sure to select the output command you want and just click Run.